Hey everyone, had myself muted there. How are we doing? Good to see you, Blake. Good to see you, Victoria. How are we doing? Everyone having a good morning? It is Monday morning, trying to get everything tech figured out. Oh, it's a crazy week. Let's wake up Mubot. Mubot's waking up. Mubot is waking up. Got my coffee. Good stuff right here. He's in the chat. He's about to be. What chapter should we do? Is chapter 8 coming up? I feel like videos are lagging, all those things. Trying to get the computer, get everything fixed. Everything. Oh my gosh. Crazy weekend. UT, what are we, 7-0 now? 7-0. What? Craziness. Craziness. How you doing, Blake? And Victoria was here. Should we do some chapter 8? When is chapter 8 due? Let's go take a look. What should we do? What shall we do? Where? Assignment manager. Assignment manager. What? Gotta open up the notepad. Thank you everyone for waiting and everyone being so positive. Didn't take quite as long to get everything fixed up and ready to go. Probably 8. What should we do in chapter 8? Chapter 8 quiz is due on the 25th tomorrow night. Woo! Tomorrow's gonna be a crazy day. Tomorrow's gonna be crazy. Tomorrow's gonna be crazy. Should we do the homework? We could do the homework right now. Try to do as much of the homework as we can. How's that sound? Let's start with the homework. The very first question, a very good place to start. And it's already a crazy question. It's already a big question. Already a question that has a lot to it. Okay, let me get Jump going here. And we'll hop in. Jump 17's out now, I think. Open license. Every time Jump. Needs to save my license. Okay, let's do some chapter 8 homework. So, chapter 8 homework. Stat 201. Chapter 8 homework. Question 1. Let's go check that out over here. So, do we need to update? Oh no, you won't need to update. We don't have you update midway through the semester. I probably won't, because if I do, I might have features you don't have. It could change the place of some buttons. Sometimes they add and remove stuff, so I wouldn't suggest updating Jump if you can get an update. I would say keep with the one you have. Jump's been pretty good, Jump 16. So what I noticed first here is we're gonna get some data. Oh, we're doing the homework. Oh my gosh. One moment. This is the quiz. That's the quiz right there. I was like, it's red for the quiz. It used to have different colors. It used to be like blue and green. Now it's like blue and red, I think. So they alert you. They're like, this is a quiz. Watch out. So we get the homework right here. Chapter 8 homework. It's like, that's a lot of questions. I mean, I already did the homework. Do you want to do a quiz question 1? We can burn through the homework real quick. So here's the homework. Here's the homework. What do you want to do, Blake? You tell me, Blake. You're here. You get to direct the conversation. So your call, Blake, on what we do. Concrete production company examines its records. Sounds good. Right. Oh my gosh. So many things. After this, could we do data analytics 6? Yeah, let's do data analytics 6. We'll do this first question here, and then let's do data analytics 6. You get data analytics 6, at least you got it. A concrete production company examines its records. The manager made the following scatter plot. The company places concrete in 2 venues. See, there's concerts and venues. A smaller and intimate theater plotted with blue circles, and a larger auditorium venue plotted with red X's, completed parts. Okay, so they're breaking it into 2 things right here. You can see one model right there and another model right there. The red model has more scatter. The blue model's tighter. Where's this going to go? Describe the relationship between talent cost and total revenue. So they both have strong positive linear relationship. There's one outlier that stands apart, maybe. Strong positive. Okay, so I think they're going strong positive. Yeah. It can't be negative, and I don't think it's weak. And there's one outlier. I mean, that's outlier in sort of the bivariate sense. Yeah. How are the results for the 2 venues? Both venues show an increase of revenue with total cost. I mean, that's, yeah, revenue goes up with total cost. That is true. Both venues show an increase of revenue with talent cost. Yeah. Both venues show that high revenue increases talent cost. No, that sounds, causes, there's cause right there. No. The cause word is cause and effect. They're going for that. Awesome. Great work. Yeah, Victoria here. We'll do it soon. How are they different? The red one has more scatter. It's high. If you put a line through this, so here, let's draw it. The red one definitely has more scatter. So if you were to go in here and add the lines and stuff, what color line are we on? Red line like that has more scatter. So this is comparing two different scatter plots. So there you go. The red line is weaker, has a maybe about a little higher slope maybe. So what's the difference? The smaller venue, which one's the smaller one? Is the red the smaller? No. The larger venue has more variability. The larger venue has greater variability. Revenue for that venue is more difficult to predict. That sounds right. Okay. Yeah, larger variability is going to be harder to predict. What they're pointing out right here, yeah, red with larger, more variability, and harder to predict. There it is right there. Great job, Blake. You're a pro at this, man. Blake's just, boom, getting those questions right there. Blake, great job. Let's throw out 1,000 points. Really good work on that, Blake. Yeah, you understand that question really well. And notice, do remember this. We're going to put this up here. Try to draw these things out. Try to understand how the relationship works, that if the points are tighter, it's going to be a stronger relationship and easier to understand the variability. So the blue graphic right there has less variability around the line. And I guess there's that one outlier they're talking about. It's extreme in its values of y and x. It kind of follows the relationship, so to say. But that's what they're getting at right here. So they're just plotting two scatter plots or two linear distributions on one graphic, and then we can add the lines to it. So you try to think, how would a line go through this data? What's the scatter around the line? The smaller venue here in blue, the larger venue in red. The red venue has more scatter, more variability. The blue has a tighter distribution. So it's easier to understand the blue distribution right there. Higher R squared for the blue. So you can come up with theoretical values. Like the blue has an R squared. This is just theoretical. Blue has R squared of like 80% of the variation. And red has R squared of something like 60% of the variation. Those are just theoretical values. You could find out the correlation then by square rooting those. But these are just theoretical ideas and understanding how it works, that the blue explains more of the variation. The red would be harder to understand because there's more spread to the data. So pretty good question. We're not going to ban that question, Blake. Let's go do some data analytics. Thank you so much, everyone, for being here. Got started a tiny bit late. Was trying to get things working. Videos were acting up. So we're going to do some data analytics now. There's my notepad. Oh my gosh. Data analytics. Stat tool 1. Data analytics 6. Ask those questions as we do it. I don't know. This semester's been crazy. I can't believe it. We're halfway. We're more than halfway done right now, right? Time flies. 2 months from now, we'll be at Christmas. A week from now, we'll be at Halloween. Halloween's on a Monday. Means I gotta dress up or do something. Yeah, it is on a Monday. Halloween's on a Monday. Anything can happen on Halloween. Your cat could turn into a dog. What the heck? Now Canvas is acting weird. Everything's acting weird. More coffee. All the coffee. Data Analytics 6 coming up this week. Decision trees. Let's go take a look at it over here. Okay. When Christmas comes, oh, cool. Coffee is good. I am addicted, Victoria. It's bad. Like, I wake up in the morning, I'm like, and I drink my coffee, and I'm like, it's like an energy bar filling up on me with each sip of coffee. So it's an addiction. Let's go take a look at some data analytics here. I need that caffeine. I don't want that caffeine. I need it. Here we go, data analytics. Let's do it. Okay, let's zoom back out on the screen here, but go make some coffee. Oh, you got it. So we're going to use the decision tree jump data right here. We're going to take a random sample of 500 plus the last two of our UTIDs. So you should have something like 523. Now, don't take 523. You should have like if your UTID is 5811 at the end or something, then it'd be 511. So make sure the last two, so you'll have 500 something. This will be your unique data set, and we should be able to see that. So let's first talk about, I think I can do that right there. I'll talk about how to take a random sample. Make sure you have JMP installed on your computer. If you have problems installing JMP, check out the videos. I think I have it in the visualization playlist on how to install JMP. So make sure you have JMP installed. And if you have JMP installed, then you're going to instantaneously go right here. That's also the visualization playlist, which has kind of general ideas how to do the visualizations. So if you want to click that and check it out, check that out. But also I'm going to show you a lot of the ideas here. Taking a random sample is not something that, you know, everyone should know how to do, and I do videos on it. So when you go to take a random sample, go here to tables and go here to subset. That's tables, subset. If you're on a Mac, the bar will appear when you go to the top of the screen with the active window being on JMP. So go ahead and click right here. Boop. And then you want to go right here and type 5 plus the last two of your UTID. Make sure it's 5 and then enter in the last two of your UTID. So 511 would be a hypothetical UTID. Now you can click OK or you can hit enter, enter. That does it too. Now you know you've done it properly if you see down there on the bottom left of the screen, all rows has 511 or whatever your 5 plus the last two of your UTID is. If you have this right here, you've done it properly. Now probably go to File, Save As. You could call this like Data Analytics 7. I think we're doing 6. Data Analytics 6 dataset. That way you just have it for future reference in case you make an error if you're watching this video now and you're like, oh no, wait a minute, I didn't do this. So make sure I do that. Okay, let's take a look at the data analytics assignment. So create a decision tree using analyze, predictive model, partition using either this or this. Now, this is talking about as the y variable of interest. The y variable of interest, there'll be one y variable in decision trees and then a bunch of x's. But there's things about the x's we should know. When doing a decision tree, we don't use these. When making a decision tree, we don't use these. What do we not use? This is the notes you should know. A lot of people say, what do I need to know for the test? Conceptual concepts like this are very important. When making decision trees, you don't use these variables. Identifiers, great job, Victoria, right there. Let's throw out some points. You don't use identifiers or things that act like identifiers. Things that act like identifiers would be things with too many levels. Now, the only things up for consideration that could have too many levels would be what variables? The only things that are up for consideration, and Victoria said so perfectly right there, categoricals with too many levels. So when you look for categorical variables, I don't think we can, darn, thought we might be able to select things via there. If you want to look at the distributions of your variables, you can look at them right here. Now, note, there's kind of a tip of where an identifier is. Here, I'll give you a hint. You ready? Talk about removing this one. You can hit delete. I delete them because I'm not going to use them. So make sure you write down what they are. That was an identifier I deleted. That is the identifier for the data set. So it's unique. It's also put in as a number. So JMP registered as a number. Identifiers are technically special case categorical variables. So we could have just called that person A, B, C, D, and then loop backed up to AA or A1, A2. We can do any sort of thing we want for identifiers, but since JMP saw a number, it said, hey, that's a number. And we're like, nah, that's their unique ID. So that was an identifier right there, unique for each and every person. That's what identifiers serve for, is just to be an identifier. They could have time ordered them other things, but at this point, that one was just an identifier. Make sure to mention removal of that. So now, what variables do we not need to consider? I see this a lot of times where people say, oh, high school GPA has a lot of levels to it. Why should high school GPA not be a variable you consider for removal? We're going through this step by why would high school, look at that, there's like 4.01, 3.5, 4.2, 4.4. Well, but does it have more than 10 levels? Does it have more than 10 levels? And I'll give you a hint right here. And I think Blake's talking about it right now. So check this out. You ready? If we have a variable like Iris has data in it, I'll show you this. This is R. And Iris has numeric factor. If I say levels of the Iris data set species, it tells me the levels. But why doesn't it tell me the levels of supple length? So just decode this riddle. Why can't I get the levels of supple length. You can delete it. I delete them. That way I don't have to worry about them. You probably are doing it right too, Victoria. You'll probably see you've done it correctly, I think, from what I'm seeing. So why does supple length not have levels? And you'll see how this relates to jump. Why does supple length not have levels where species does? Why does supple length not have levels? Because supple length is this. Because supple length is this. Supple length is this. That's a hint. And there's only two types of variables beyond identifiers. Supple length is a what type of variable? Supple length. How long is the supple? Whatever supple is. It's quantitative. Roshni getting us 1,000 points. It's quantitative, exactly. So the idea of levels doesn't apply to quantitative variables. So is high school GPA okay? Yes or no? It's got lots of different values, we could say. Does high school GPA have too many levels? It's a bit of a trick question. It's a bit of a trick question. But just think about what you just saw. And high school GPA is also this. And then I'll explain. But don't worry about getting it wrong. But I want you to have that moment where you're like, oh, okay. And then you know which ones to look at in here. So does high school GPA have too many levels? Thoughts on that? Oh, so great job. Good, Victoria, 1,000 points. Don't worry. The answer is the idea of levels does not apply because it's a quantitative variable. Does that make sense? Levels only applies to categorical variables. So relationship status has levels: single, dating exclusive, dating one person, and engaged. But for high school GPA, because it's blue, meaning quantitative, that means the idea of levels don't apply. Just like over here in the other program, the idea of levels to a quantitative variable doesn't apply, but categorical variables, that's what a factor is, applies. So the only ones we need to check are the ones that are what? The only ones we really need to care about are the ones that are what color. Like, should I look at number of pets owned or number of pet expense and be like, ooh, that's got lots of values? Should I care about yearly pet expense? Yes or no? It's blue. So should I look at blue? Should I care about blue? Yes or no? So blue means what in jump? Correct. No. 1,000 points again, Victoria. Excellent work. Blue means no. I shouldn't. It's quantitative. The idea of levels doesn't apply. Do you maybe start to see thing? Well, these aren't identifiers. Good answer, Blake, right there. Numeric values could be used as identifiers, but none of these. I'll tell you that hint right now. There's only one identifier at the start. Make sure to tell that one was removed. But then maybe start to see things with too many levels, right? You go what I'm getting at? Dropping some major hints. Do you get what I'm getting at? Where things that could have too many levels with more than 10. You get what I'm getting at? So so don't even worry about those exactly. And then look at the red ones that maybe have too many levels. Make sure to mention those. And then remember, 10 or more is considered too many levels. So if you have something like sibling order, does that have too many levels? Sibling orders is categorical. Like, what is your sibling order? I am in the middle. There's youngest, oldest, only, and in the middle. So with sibling order, is there too many levels? Yes or no? No, there's not. There's 4 levels. That's not too many. Some of them might have too many levels. Remember the ones we're looking at as red. Great job, Roshni and Blake right there, and Victoria. So make sure to go through these, look through, see if you see anything. I'm just so make sure to identify them and remove them. If you see something, don't remove Greek life, but if you see something, mark it down, mention it was removed, and you can click on it and you can just delete it. Now, don't delete Greek life, but you can just delete it. Well, when leveling up, your measure is as a quote. Is there an easy way to see how many levels there are? You can view it this way to see how many there are. You see, this has 132 additional levels that are not being displayed. There might be. I can do it in R really quickly. That's the problem, is like I can easily do that in R. In R, the code would be length of levels. And then, oh, you see that doesn't have levels. So there's the code in R to find out that has 3 levels. I know, right? So, and then I could loop that over all the vectors, or I could use and apply to categorical columns and figure out which ones have, and I could do a true false and remove the ones. So I could literally write the code to have it do it for me, which is so great about coding. Other than visually inspecting, I'm trying to think. You can also go to Analyze, Distribution, drop them all over here in the Y. This is going to do the same thing, but just give you more output. So then you could scroll through here. Does that make sense, Blake? That was Analyze, Distribution, and grab all the variables. And then you could see if you see something with too many levels. Also, to limit your output, so I'll do it a little more slowly here, go to Analyze, Distribution. Under Distribution, click the red arrow and deselect Numeric, because we only need to check what columns. We only need to check what columns. We only need to check what columns. We only need to check what to see if they have too many levels. What variables to see if they have too many levels. The red ones, the categoricals. So now I've clicked Control A for select all, or Command A on a Mac. Drag them all over, and then you have now created bar charts for everything. You could click stack or scroll through. Like, how many levels does dating have? So count the levels. Be careful. How many levels does dating have? Dating or relationship status has how many levels? Great job, Roshni. How many levels does relationship status have? Oh, literally. There you go, Blake. I mean, it says right there. I was wondering if people would count the last thing, but it does say 4 levels right there. So you can actually go through and see how many levels. So I don't know of a good way to aggregate those, but you can go through and see how many levels there are. So Jump does tell you at the bottom, and you can see how many levels they all have. And hopefully you see what I saw. So I saw 2, I think, my quick glance, 2 additional ones other than the identifier. Okay, so we've done all of that right there. We've talked about what needs to be removed. Okay, so specific variables which should be excluded. Take 3 splits of your decision tree. Yeah, Ivana, good to see you here. Ask any questions you got. So now you're using O2 or O3. Should we do a categorical or quantitative tree? I think, yeah. It'll still, yeah, it'd be really hard. Good question, Blake. I think it'd be impossible not to get. Maybe there's like one theoretical way you could get it, but it'd be nearly impossible. But you should have like 10 levels. So, should we do a categorical or quantitative tree? Because this is a quantitative tree. We didn't do one of those in class yet. Or start class today with that. And this is a categorical tree. So what do you want to do? A categorical tree, which we did a lot of during class, or a new quantitative tree? Which one should we do? The analysis is a little different. In this one, you analyze differences in means. This one, you analyze percentage in each group. So should we do a quantitative or categorical tree? Whichever one, just put C or Q in the chat. We won't do the O3. We won't do the O2 tree. We'll just do data related to it. What should we do? Categorical or quantitative? So you have to know the 2 analyses right here. Categorical, let's do categorical, which would be similar to doing gender. So let's go over here and go to our data. And we got the data open. Now we're going to go to Analyze, Fit Y by X. Analyze, Fit Y by X. I'm going to put in here making the tree. Getting started. And we're putting another timestamp in here. 25, 4 to 3. Stat 201, making, or data analytics 6. Data analytics 6, making the tree. Okay. So with this, we are going to do the following. Now you're doing O2 or O3. You want to click Control or Command A. With this, you want to now take and drag everything into the X. I know we're bringing the Y over there, but just wait. Just wait. Now that we have everything over there in the X, we're going to select our Y variable of interest. So I'm going to take, you're going to take O2 or O3, one of those. I'm going to take, if someone's in Greek life. Does that make sense? I am taking if someone is in Greek life, which is a categorical Y that I'm going to predict. Click it one time, let go, and then bring it up here. Don't click and drag or you'll do that. You click it one time, let go, and then drag it up there. A lot of people click and drag. Once again, click, let go, and then bring up to the top. Now that we have it up here, this is our 1y variable. I want to know why people are in Greek life. Why are you in Greek life? Well, maybe these things down here explain it. We're going to click OK, and the tree is going to be created right here. Ooh, I really just went to the wrong platform. Analyze, predictive modeling, partition. Sorry, if everyone followed along, they just got what I got. This is analyze, predictive modeling, partition. Analyze, predictive modeling, partition. I went to fit y by x. Analyze, predictive modeling, partition. Let me advance that. Analyze, predictive modeling, partition. Analyze, predictive modeling, partition. Same procedure. I put a new timestamp here. So we went to analyze, predictive modeling, partition. We're going to click Control A or Command A to select all the data. And now you've got all the data selected. Now you're going to click and drag into the X right here. Now that you've brought them all over to the X, you're going to take either O2 or O3, depending on if you want to do a categorical or quantitative tree. I'm going to pick Greek life. I'm clicking it one time, and then I'm dragging it up here. So make sure to click, let go, and then drag. If you click and drag, it'll pull and create a window. But if you click one time and let go, you can actually move the one variable by itself. Remember, you are doing O2 or O3. Do not do Greek life, or you might not get a good grade. They could say, hey, you did the wrong variable. I'm just doing it to do analogous work. So here we go. Click OK. Now, what does this look like right now? If you did a quantitative variable, it'll look different because it'll analyze the means. If I click color points, maybe it looks something more like you've seen before. What kind of graphic does this look like on the screen currently? What kind of graphic does this look like on the screen currently? It looks a lot like a what graphic? What graphic does that look like? Not good guess right there. Not residual, but mosaic, like a mosaic plot. Good guess right there, Blake. And let's throw everyone 1,000 points for being here. Keep up the work. It looks a lot like a mosaic plot. A residual plot would have the line going through it, which would show us, oh, I guess because that line right there. So that's not like a flat line at 0. That is the dividing right there telling us 20, something like 28% or something of people are in Greek life and 72% are not. We could actually go right here and click the red arrow and go to leaf report. And I said 2872. And no, it's 32 to 68 about. Does that make sense? 32% of people, if you look up here, 32% of people are in Greek life. 68%, I'm rounding it, are not. So there's the splits right there. We can see how many right here with 166 and 345 out of the 511. So this is our only leaf right here. Great job right there, Blake. And let's click the split. And what do we notice first? What is the most important variable in determining if you are in Greek life? Look at where the blue went. The blue means they're in Greek life. What was the most important variable in determining if you're in Greek life? And we can see if this tree works for you if you want. Only if you want. The distance you are from campus. People who are on campus or a walking distance from campus. So if they're on campus or they can walk to campus, they're more likely to be in Greek life. You can see it up here in the top because this is leaf 1. It goes 1, 2, 1, 2, 1, 2. The first leaf has 192 people not in Greek life, 137 in Greek life. 40%, it split the people over here. That's about 40%. And that's about 60% or 59%, 58% technically. And then over here, less people are in Greek life who are under a 10-minute drive, 10 to 30-minute drive, 30 plus. This means they are in one of these categories. Like, I am a 30-plus minute drive from campus. I am in this category, and I'm not in Greek life. So now let's click split again. And the next split over here is, oh no, oh no. The next split is, how many times have you cheated in college? Ay, ay, ay. So, remember, this doesn't mean it has to be this way, but this is the way the tree went. Data's going to do what data does. Let's split the tree again for the last split on the tree. And this is how many weekly hours do you work? And so the most likely individuals to be in Greek life are going to follow this path here where the blue goes. This is just data. Just data. Data does what data wants. That's what data do. The least like, what's interesting is, you know, right here, these are the people least likely to be in Greek life. All 7 of these people, you see the 7 right here? That's 7 people. You might say that's 7 people. That's 7 people in leaf 2. Do you see why this is leaf 2 right here? 1, 2, 3, 4. Now watch when I go up to the graphic. This little tiny little sliver right there, you can barely see it. 1, 2. There's 7 blue dots in there. 1, 2, 3, 4, 5, 6, 7. There's 7 blue dots in there. So you can see right here, none of those people. Oh, I was on the wrong thing. 1, 2, 3, 4, 5, 6, 7. None of those people are in. Looks red to me. And they're not in. That means they're not in Greek life. Leaf 1 is where the Greek life is. Leaf 3 is also Greek life, which is funny. So you might say, well, what does this point to? Well, you also have a bunch of people over here who are in Greek life. So there are people here in Greek life, people here in Greek life, people here in Greek life. And so there's a lot of different people, a lot of different variation. Oh, the Greek life are, did I mess up? These are the not Greek life. This is the not Greek life. Red is not Greek life. Blue is Greek life. This is most likely the Greek life. This is least likely Greek life. Does that make sense how I can see that visually? Like the one with the most blue is most likely Greek life. The way it does the calculations on the numbers sometimes is a bit interesting to me. It should be 100%, but I think Jump is using like estimates and predictions based on averages throughout the tree. So it kind of does a probabilistic thing. I use these percentages to talk about, but it's weird because you see 7 and 0. You'd think it'd be 100 and 0. But I don't know. Jump does an advanced calculation on that to make predictions at the end of the tree on weighted averages throughout, I believe. So with this right here, we usually just use these percentages to talk about what would be expected at the bottom of the tree based on the past data right here, because this is only a subset of this going down further. And so we have leaf 1, leaf 2, leaf 3, leaf 4, leaf 1, leaf 2, leaf 3, leaf 4, leaf 1, leaf 2, leaf 3, leaf 4. Up at the top, leaf 1, leaf 2, leaf 3, leaf 4, leaf 1, leaf 2, leaf 3, leaf 4. Now, if you want, you can hit Control Shift- or View, I believe it is on here. Where is it? There it is, View. You can view and go to zoom in or zoom out. I'm hitting Control Shift- or Control Shift+. That's Command Shift- on a Mac, and you want to take screenshots of this. Make sure to take screenshots. You can make this smaller. I wouldn't make it that big. You can take a screenshot of this. So you want to make sure you have your screenshots. Screenshot 1. Screenshot 2. If you had to take multiple, it's all right. And then screenshot 3 down here. And it might want the R squared. But let's look at the R squared. The R squared is under split history. So under split history, we get the split history of the R squared. So you want the splits to be most, well, you're going to be able to see, and I like to increase this a little bit right here so we can see the R squared going up. I will be able to just, yes, 100%. Max can 100% do this. This is the increase in the R squared. I guess we want to start at 0. This is the increase of R squared over history of the tree. I'm not going to extend any further. So the R squared went up from about 6% to under 12%. And I would even throw this on there. Nothing wrong with showing the split history to show the increase of R squared as we continue to split the tree, which is how much of the variation we explained. So there's our screenshots. Let's look at what it asked and try to answer it. Your screenshot of the output must include the decision tree and the leaf report. So we took all those. You don't need the split history, but nothing wrong with knowing what split history is to know it's the increase of R squared over time. The names of the predictive variables that were excluded, we went over that. So those were the ones that had too many levels. Remember, we took out the ones with too many levels, and we took out the identifier. Depending on your response variable, choose either describe the characteristics of the students who are the youngest on average, include the that's for the quantitative on age, or describe the characteristics of the students most likely to be female, include the number of students and proportion for this group. Where would you get the number and proportions from? When it says include the numbers and proportions, where would you get that data from? When you look at the numbers and proportions, where would you get that data from? When it says get the numbers and proportions, where would you get that data from? When it says include the numbers and proportions, where would we get that data from? Where do we get the numbers and proportions from? The leaf report. The leaf report shows the proportions and the numbers. And the reason it looks this way is because we have a categorical variable. Now, I want to point something out right here. When you are doing this, if you want to talk about the most and the least likely group, the easiest way, I'm going to do a totally different variable. The easiest way to talk about the most likely group is to look. Ooh, why do we still have major? Oh, I didn't delete them off. Yeah. Let's look at student loans. So this would be the most likely person to have student loans I'm going to look at. About half of students have student loans, a little less than half. So who would be the most likely person? Yes means you have student loans. So which leaf? First off, look at this visually and tell me which leaf. Leaf 1, leaf 2. Remember, blue means yes. Blue means yes. See how yes is there, and if blue is up top. Which leaf, 1, 2, 3, or 4, is the most likely to have student loans visually? Look visually first. Leaf 1, leaf 2, leaf 3, leaf 4 is the most likely to have student loans. Which leaf is the most likely to have student loans? Just look visually first. So visually speaking, which leaf is the most likely to have student loans? Just look visually first. Remember, blue means yes. So which leaf is the most likely? The leaves are the very end of the tree. Well, but that's their only one characteristic. You have to follow the tree down to there. So that, Blake, you're on the right track. So remember, when you do the tree, they're going to follow this path. It's like driving a road, and you're going to go down to here. So you're going to follow the tree down because it's a tree, and these are the leaves here at the end of the tree. So you're going to follow the tree to the leaves at the end. So leaf 1, So, but that's not everything about them, right? So if you want to learn about leaf 1, you can actually go down here and look at the leaf report. So the leaf report, you can literally read across it. So that's only one characteristic about them. So leaf 1. So write me a full sentence about them. Like, just try writing this sentence. We see that 88.19% of them have student loans, which is 33 of them have student loans and 4 of them don't. So these are the percentages. Because that's still leaf 1 down there. It's just another way to talk about it. Leaf 1, leaf 2, leaf 3, leaf 4. Leaf 1, leaf 2, leaf 3, leaf 4. Can you tell me, what all can you tell me about them? What all can you tell me about them? Their family economic status. Their family economic status is lower middle, lower class, or middle class. They're one of those. So they're middle class or lower. They are fluent in less than 3 languages, and they work 24 or more hours a week. So it sounds like to me this is a person, like we said, middle or lower class, who is not fluent in a ton of languages. So they're probably a national born, like within America. Well, but no, like that's just one characteristic of them. That's just one thing. So that's just the last thing at the end. So this is they have to go down the tree totally. Does that make sense? Don't worry, this is good practice right here. I'm glad we're talking about this. You have to pass through the tree this way. You have to pass through down to the bottom. So you have to say, okay, they're lower middle, lower or middle class. They meet that criteria. Their number of languages fluent in is less than 3, and they work 24 or more hours a week. So they meet all these criteria. There's 37 people who meet all these criterias. So, like, let me try a totally different way. I think this might help. You ready? Blake, and it's okay. Do you want to go through a tree right here? I'll try to make sure the questions aren't too personal, and I'll show you how the tree works because I think it makes more sense. Blake, do you want me to predict if you've broken a bone? So there's another categorical variable. So Blake, do you want me? Oh, of course it puts that there. I'm not going to ask that. So, it should all be one sentence. Okay. Well, now it's asking politics. All right. So I'm not answering for myself. Okay, where is it? Okay, I'll do this. Okay, I'm gonna predict if Brian's broken a bone. You ready? I'm gonna run through this tree. That's the log likelihood. Don't worry about the log likelihood. It's a way of looking at the p-value, I believe, to tell you how significant the p-value is. Don't worry about that in the analysis. So with this right here, what we have is the first question we ask of Brian is, have you been arrested, Brian? I'm going to answer the true myself. So no, I've not been arrested. When did I first drink alcohol? And so if I either answer grade 10 or 19 or I don't answer, then like this one, when did you have your first alcoholic drink? Then that is, I'm going to go here with this path. And I had one in high school because Richie, sorry, Richie, you broke the law. I think you're a lawyer now. So less than 19. Yeah. So I'm over here. And then what is my gender? I am male. So with this right here, I said I haven't been arrested. I had a drink of alcohol in high school, and I am male, so I'm right here. I am in leaf 3. It's not because I'm male. Like, you don't just go to the bottom and look at the bottom question. You have to go down the tree. You start right here with the first question. Does that make sense? And I won't ask anyone else this tree. It's a little bit personal right here. I don't mind, but does that make sense, Blake? When you go through the tree to see where you're at, you have to start at the very top, and you go down each question to see if you meet the criteria to be in the bottom leaf. So they're called terminal leaves because you go down the tree, you go through the tree. Let's look at a quantitative tree because we haven't done that analysis yet. So let me do the same sort of thing right here, but do it with a quantitative tree. Now in quantitative trees, it's the exact same thing. It's a really good, tomorrow we're going to be doing a bunch of chapter 8. So let's make making the categorical tree. Making the categorical tree. Let's make a quantitative tree. Makes sense. I guess I'm still curious how a sentence would look and when you get the numeric values. Okay, so here we go. Let me explain right here. To get the numeric values, we go to the what? Brian, why aren't there more sections of... Oh, thank you, Natalie. Oh, well, sometimes they open up. Sometimes they open up more seats. Be honored to have you, Natalie. Thank you, Natalie. It's very kind of you to say that. Where do we go to find out the amount of people in the leaf? And we're looking for the people most likely to have broken a bone. Most likely to have broken a bone, let's say. The people most likely to... How would we find that out? I mean, you can kind of see it visually. Blue means broken a bone. So you can see here leaf 1, which is this, has the people most likely to have broken a bone. So where would we go to see how many people are there? There's 28 people right here. Where would I go to see the amount of people in this and the percentages? Where do I go to see the amounts and the percentages? What output do I make to see that? What output do I make to see in these leaves how many people there are? I go to the leaf report. Boop. So remember, it's leaf 1. Now this is easy. Leaf 1, 80% of the people have been arrested, which is, 80% of the people, we're talking about the Y variable of interest. 80% of the people have broken a bone. That's the Y variable of interest. So the yes right here is for the Y variable of interest. Have you broken a bone? You see how it's broken bone? Yes, no. That's what we're looking at right here. Yes, no. And this is leaf 1 with have you been arrested was the X variable we asked them. Notice how have you been arrested, it's very hard to see right there, is the X variable. So all you have to say is if somebody's been arrested, we saw that 80.88% of them have broken a bone. 23 of them did and 5 of them did not, which is out of the 28 people. Now, the people least likely to have broken a bone, least likely, are in leaf what? Leaf 1, 2, 3, or 4 are the people least likely to have broken a bone. Look at the output right here. Tell me leaf 1, leaf 2, leaf 3, or leaf 4. Remember, the leaves are the terminal ends of the tree. So leaf 1, leaf 2, 3, or 4 is the least likely to have broken a bone. Leaf 1, leaf 2, leaf 3, or leaf 4. Which ones are least? 2. Great job, Blake, right there. So leaf 2 is the least likely. So what you can actually do is you can go down here to leaf 2. You see how this is the second in the output. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Also, it is up here on 2. Notice all the red. So with this, we could say the people who are least likely to have broken a bone reported for being arrested, no. You see how I'm just reading across? They reported for being arrested, no. And the age of first drink they reported was greater than or equal to 19 or missing. Do you see how I'm just reading across that right there, Blake? Does that make sense? Which is the same thing as going down the tree by saying been arrested, no, and age of first alcoholic drink is greater than or equal to 19 or missing. Leaf 2 right here, if you read across it, you can actually get the pathway down by just reading across. There were 72% of them, or 73 rounding up, 73% of them did not break a bone, which is 70 out of the 96. Just understanding the numbers and where they come from is very important with this. How does that look, Blake? And we'll do a quantitative tree here next. But does that make sense how you can just read across this to say the people least likely to have broken a bone? Remember, we're just looking where all the red is at in the terminal leaf. The people least likely to have broken a bone reported being arrested, no. And the age of first alcoholic drink was greater than or equal to 19 or missing. All I'm doing is reading across this right here, which is the same thing as going down the tree. The most likely to have broken a bone was the easiest because it was just one split, which didn't have any kind of sub-splits afterwards. How's that looking? Does it make sense how to know which ones have the most and least? And the leaf report's going to give you those numbers right there. What we can also do is we can make a quantitative tree. Let's do a quantitative, which we're going to do at the start of class today to review. And to make a quantitative tree, I'm just going to go and let me put the note in the quantitative tree. So if you were to do age, the quantitative tree is very, very similar. I'm not going to do age. Let's do how much you work. Cool. So how much you work is a quantitative variable. Why? And we're going to go to rows and go to clear row states so the colors are gone. What do you think this represents down here? 1,000 points if anyone can tell me. What do you think this represents? Why is that all across the bottom right there? Like, what does that visually mean? So look where it's at. And then look what the question was. What does that visually mean on the Y scale? What does that visually mean? What does that mean? Let me get the timer going. Just saw I had 20 minutes. There we go. What does that visually mean? That means there are, and we highlighted it, 287 if I highlighted everybody. I think I missed one person over there. There's about a little less than 300 students who work 0 hours, because this is the question of how many weekly hours do you work at your job, and these are the students who answered 0, and up here are students who answered more than 40, and the average for students' weekly hours worked was 70 or 7.89, and 511 students answered the question. So we have 511 because that was our sample size, and we have 7.88. Good to see you here, Evan. Evan and Blake are here. Yeah. So that is what the data means right there. The standard deviation is the variation. This is a very right skew distribution. You can see the build up here at the low number and then working on the decision tree. And so now let's split it. And the best variable for understanding how much somebody works is what? Well, we might start that later today. The best variable for determining how much somebody works is what? The best variable, which is our first split, usually dictates the best variable because it's the first one, like that decides it. This explains about 8% of the variation. The best variable for determining how much somebody works is what? It's interesting because you can group this into two things. The best variable is how far do you live from campus? So think about this. We have people who live on campus or walking distance. I think that's one thing right there. No, it's two. It's on campus or walking distance. And then we have people who are kind of a drive. So we have two groups right here. We have people who are basically on campus or can walk to campus. And then we have people who have to drive, like under a 10-minute drive, 30-plus minute drive, 10 to 30-minute drive. So people who have to drive to campus. So this is don't have to drive to campus, do have to drive. So maybe having a car, right? Something like that. Like if you have to drive to campus, you have to have a car or transport. So, yeah. And your sibling order is the next variable. I don't know. So middle child. I didn't work that much in college, so I don't know. And then student loans. Okay, the people who work the most right here would be who? Who works the most? Leaf 1, leaf 2, leaf 3, or leaf 4? Who works the most? Leaf 1, leaf 2, leaf 3, or leaf 4? And check it out. The leaf report's a lot easier to look at. Leaf 1, leaf 2, leaf 3, or leaf 4 work the most. And you're getting the mean, which is the average for these groups of individuals, these 80 people, these 102 people, these 70 people, these 259 people. Which leaf works the most? Leaf 1 or leaf 2, leaf 3 or leaf 4? Leaf 1. Leaf 1 works the least. Good work. Good guess there, Evan. Leaf 1 only works 4.47 hours. We're throwing 1,000 points. Leaf 1 only works 4.47 hours. It has the most individuals in it. So there were 259 people in Leaf 1 who had an average amount of work of 4.47. The mean, So now we go to Leaf 4, and this is just how many people meet this criteria. The count right there is the amount of individuals there are in the leaf, as in there are, and it's really hard to see in that, but there's 102 people who are some driving distance from campus and have student loans, and the average amount of work for those 102 people is 12.54. The amount of variation explained by this tree is 13.5% of the variation, so there's extra variation. But does that make sense how to read this right here? If you look at the terminal leaves right here, you can see that leaf number 4, the log worth is that's the G squared right there. It's the statistical significance. I think what it is it takes the p-value and does it by like e to the negative 10 or whatever, or e to the negative 1. And so the higher the log worth, the more statistically significant the split. I think I've hovered over it before, and it tells you about log worth being the statistical significance of the p-value. So yeah, you're not going to analyze it in this class. So that's a statistically significant split. That's a statistically significant split. I think you need a log worth of about 2. So that is barely statistically significant. Barely. Maybe. I don't deal with it so much. So each terminal end is a leaf. Do you see how there's 4 leaves right here? Leaf 1, leaf 2, leaf 3, leaf 4. Leaf 1, leaf 2, leaf 3, leaf 4. Harder to see up here, but it puts bars right here where the leaf ends. Leaf 1, leaf 2. So hard to tell. I always hate looking at these up in the visual. But it's easier to tell if you're over here in a categorical tree, which is going to make it so you see what color the points, or we can't now. Redo. Color points. There you go. Leaf 1, leaf 2, leaf 3, leaf 4. Leaf 1, leaf 2, leaf 3, leaf 4. Leaf 1, leaf 2, leaf 3, leaf 4. Now I'm going to do a really hard question that people get wrong on the test. What are you confused on, Blake? Let me know what you're confused on. Really hard test question, then we'll end off here. Oh, Tableau is opening up. Tableau, go away. Okay. Let me put here in the notes, really tough test question. Decision tree test question. Okay. I'm going to make this really tough. If you can get this, you pretty much, but you're saying that not every box is correct. Only the ones at the end. Think about how a tree looks. Where are the leaves on a tree? If you think about the leaves on a tree, so this is a tree, right? Where are the leaves on a tree? Where are the leaves on a tree? At the ends, right? So if this is a tree, it's kind of upside down right now. But if this is a tree, there's nothing after the leaf. Does that make sense? The leaf is at the end. So when we talk about the leaf report, does that make sense? So the leaves on a tree are the very end. So those are the 4 leaves. Leaf 1, leaf 2, leaf 3, leaf 4. You read them from left to right. If there's nothing after it, it's a leaf. So down here, when you look at this is the leaf report. Leaf 1, leaf 2, leaf 3, leaf 4, leaf 1, leaf 2, leaf 3, leaf 4. Which of these leaves, this is an easier question, has the least amount of people in it? Which of these leaves has the least amount of people in it? Look at the numbers. Which of these leaves has the least amount of people in it? 1, 2, 3, or 4. I wouldn't look up here at this because these are the percentages, but which leaf, 1, 2, 3, or 4, has the least amount of people in it? This is an easier question. Tea leaves, like, Do you see how that's the skinniest? Notice here it's the skinniest. You can actually tell leaf 4 looks to have the most, and you can see leaf 4 has 225. You can see 28 people, and the 28 people are 23 and 5. You can actually count the 5 red dots right there. 1, 2, 3, 4, 5. They're all clustered. But there are 5 red dots. So here's the really hard test question. Are you ready? This is a tougher one. I'm going to show you how to solve it. We got 13 minutes, but we're going to probably end in about 5 minutes because I got to start class here soon. what percent of people who have not been arrested have broken a bone? We asked, have you broken a bone? What percent of people who have not been arrested have broken a bone? I'm asking about this blue right here. What percent of people? So now be very careful. What terminal leaves go into this? This is a tough test question that a lot of people, it goes to you, do you really know how to read this output, and can you bring it back up? So what terminal leaves go into this right here? This is the easy way to solve it. You see how there's 483 people? We're asking for the amount of blue there is, not quite the percent. We could do the percent or the number. I think I asked the percent first. Either one could be the question. Like, what percent of people who have not broken a bone what percent of people who have not been arrested? Yeah, I meant to say broken a bone, right? What percent of people who have not been arrested have broken a bone? Yeah, that's what I meant to say. So what terminal leaves go into that? What terminal leaves go into that? I call them terminal leaves sometimes just to like make it more clear that we're talking about the very ends. So which ones go into that? Remember, it goes green. 1, 2, 3, and 4. So it's 2, 3, and 4, right? So now when you look at this down here, this is the output you're thinking about. Does that make sense? Following me so far? So how many individuals are there who have broken a bone? How many? How many individuals are there who have broken a bone? How many? How many? That might be right there. That looks right. That is correct. Great job, Evan, right there. So what did you do? I think you're doing, I'll show you what Evan's doing. That is correct. 210 right there, Evan. He's taking 26 because he's adding up these numbers, plus 94, plus 90, because he's just adding up how many people there are and leaves 2, leaves 3, leaves 4, because they're all going to go back into this. And then what do you do to find out the percent? To find out the percent, what would you do? Because now you know up here, that blue area is 210. To find the percent, yep, you're figuring out. To find the percent, great work. What do you do now? To find the percent, you do what? Oh, we got to send out class in 10 minutes. 2 seconds. Let me send that. Class in 10 minutes. Oh, I hope we got everybody today. Class in 10 minutes. Class in 9 minutes. Class in 9 minutes. Big bonus. New intro. See you soon. Click here. Okay. There we go. And there's that. Okay. That's correct. When is the draw for that? Yes, we're doing that after this weekend. Yeah, it's like sweatshirt hoodie things, which I'm excited for. I talked to my boss, and he said after this weekend, and thank you for all the kind comments. One person even said like Jason rocks. But yep. And so 210 divided by 43, that'd be the percent right there. Yep. So there were 210 people who have not been arrested or broken a bone, and 210 divided by 483 is the percent. And I'm actually going to do the drawing in front of him. And so that way he sees it and he knows that we didn't purposely pick anybody. I'm having him do it. Like, I'm having him watch it. So and then if people don't respond within like a week or something, then we'll probably try to give them out to other people. I think we got a lot. I think we got like 10 or 20. Shout out to Mark Willoughby right there, I think he gave them to us. But so exciting stuff. I think it has some swag right there. With that, we'll be back here next time. Bye for now, everyone. Bye.